Hello, people. Let's talk about conductors, which is to say any old wire and its resistance. Because as you know, there is no such thing as a perfect conductor. All right, every conductor, every wire does have some resistance, and the wires or any wire's resistance depends on a couple of physical characteristics. One of them, well, so let's draw for ourselves uh, a wire, a nice cylindrical wire. All right, and this wire has some measurable characteristics, quantities that affect its resistance, and one of them is how long it is. Whoops. Fine. Length. Right? So length L measured in meters. All right? Then there's this, which we call cross-sectional area, variable A, measured in square meters. Well, those are the two big physical variables that affect the two, I don't know, spatial variables, I guess, that affect this wire's resistance. How long it is, and you sort of say like how thick it is, right? And the way it works is, well, longer wires have more resistance, right? Which suggests, and it actually is the way it works, that resistance is proportional to a conductor's length. All right. Cross-sectional area works the other way. Bigger, fatter wires, wider, thicker wires have smaller resistance, which suggests that, and what it actually is that resistance is inversely proportional to area. And this suggests that, well, resistance equals, I could say, is proportional to, how about that, L over A. Fact, that's true. But it's not true that every single wire of the same length and same cross-sectional area has the same resistance, because there's other stuff about different wires, and one of those is what the wire is made of. And we capture that in a quantity called resistivity. And that's a characteristic of what the conductor is made of. All right, we use there a lowercase Greek rho. It's got some funky units, we'll talk about that, but the deal is the bigger, sorry, I should do this. Its variable is rho. It's measured in units we're going to get to in a second. And this just says, well, that bigger resistivity means bigger resistance. Not the same thing, not the same quantity, not the same word even, if you look closely. This doesn't say resistance, it says resistivity. And it happens that resistance is proportional to resistivity. And actually what does happen is we just turn this, well, I'll leave that. Resistance is proportional to that. Resistance is equal to what physics folks say, rho L over A. Rho L over A. Now this says that this works at constant temperature. Because temperature is another characteristic that can affect conductors' resistance. There are things called superconductors, which have really, really low resistance. In order to make conductors superconductors, they have to be super duper cold. So this does say that high temperature means high resistance. That's just sort of a maybe qualitative thing you ought to be comfortable with, but we don't employ it mathematically. Okay? Yeah, so there's that. That's it. Okay, those are the factors that affect a resistor's or a conductor's resistance. Its length, its cross-sectional area, the material, the material's characteristic resistivity, and the temperature. All right? But again, we don't really worry mathematically about temperature other than qualitatively to say that hotter means more resistance. Now the resistivity thing, notice we can solve this equation for rho, and we get rho is RA over L, which means that rho is measured in ohms, meters squared per meter. But why wouldn't we just say that that's ohm meters? And that's what we say. Resistivity measured in ohm meters. All right. On the Regents reference table, there are a few typical. A few typical. There they are. Resistivities. Notice at 20 degrees Celsius, which is to say at about room temperature. Those are resistivities of some common conductors. The most common conductor that we use being copper. Okay. Yep. That's pretty much it, folks. Okay. Fuel, that copper one you ought to write down. You're going to need that. 1.72 times 10 to the negative 8th ohm meters. All right, so with this, with your newfound, equipped with this new knowledge, here's what you're going to do for half of today. You have this activity. Somewhere. And if you don't, there's probably a few extras. And, well, here's some talking to do. You're going to do two things. Now, I know that yours says 10 gauge, but I changed it to 14 gauge. The 14 gauge stuff is there's 4 of them around the room, and they're on the order of 1 meter long, and they're coated in white insulation, white plasticky insulation. But it is fairly heavy stuff, and I changed this too. What the 14 gauge stuff is used for is household wiring inside the walls of your house. You'll find a lot of that, or maybe 12 gauge, but it doesn't matter. And your job is to find the resistance of a single bare, what's called the ground wire. There's one uncoated copper wire. You got to find its resistance. I'd like you to do it 2 ways. One way is to make all the measurements you would need to calculate resistance. Measure length, measure cross-sectional area, and you know what the resistivity is because it's copper. All right, and with that, calculate what the resistance of that wire is. Now, you can confirm that, or at least compare it to a directly measured value of resistance, because you can use a multimeter as an ohm meter, right? And what I'll suggest there is when you use the multimeter as an ohm meter, don't use any leads, because the leads, being wires, are resistors. So just take the wire itself and plug it directly into the ohm meter, or the multimeter that you set up as an ohm meter. Be careful with that. And just make sure that the wire makes good metal-to-metal contact inside the meter. Okay? The resistances you measure should be less than 1 ohm. I mean, duh, they better be small resistances, right? So here, you'll have a calculated, notice, this is different. I understand it's different than what it says on yours, but I updated it. you should compare measured and calculated values. Okay? Activity 2 is to find the resistivity of some real skinny wire. There's 22 gauge wire, which is the really skinny stuff. There are some long sections of it around the room, and there are some tape measures you can use to measure long stuff. So same thing, measure the length, measure the cross-sectional area. This one you have to measure the resistance of with an ohm meter, and then you'll calculate the resistivity. Okay? Now, as far as measuring cross-sectional area, let me hang on a sec. To do that, you're going to use what's called a dial caliper, which looks exactly, it's this model, it looks exactly like this. All right, and what you do is you use a little, what's called the thumb screw here, and turn that thumb screw until it pinches the wire between these two jaws. All right, and this little indicator will wheel around, indicating how many, I know it's hard to see, but how many thousandths of inches there are between the two jaws. All right, notice this is 100, but since each one of them is 1,000th, when this needle goes around once, that's 100 thousandths of an inch, which is to say 1/10 of an inch. All right. These little tiny numbers here, when this thing is, if you close it all the way down and get to 0, when this has gone around once, which is to say 1/10 of an inch, you'll get to a number 1 right here. And so you squeeze this thing around the, around the bare wire, and you read its diameter in inches, which you'll need to convert to centimeters, and then to meters, and then find area. Okay? But notice, I mean, we get down to, this reading says, well, I don't know what number of tenths we're at, but this is 0.1, looks like 0.18, well, and even a little north of 0.18. So this could be like, let's say, actually, it looks to me like this is 1 inch, so 1.1181 maybe? Super duper precise. Your measurements really should have 4 decimal places, down to the 10,000th of an inch. Super duper precise. Embrace precision, people, when you can. Why not? So yeah, these dial calipers, there are a few of them around the room. Be careful with them. If they break, it's your fault. Don't break them. And that's that. Okay? That is due on Monday. The resistance and resistivity activity. Also due on Monday, why don't we say, there's something I put on Edmodo. It looks like this. There are some review problems for your next week's test retake on momentum. And here they are. So this is on Edmodo. And I would say by Monday, why don't you also have, I'd say let's also have the first 3 of these. Let's call it the first 2 of them done. This one and this one. This one and this one. Okay? Answers are here in parentheses. Those are answers. All right, folks. Bye.